Hello, AP Chemistry people. They have officially kicked me out of the school, at least for now, which makes demos really easy to do. I'll just use salt and vinegar for everything because that's, I'm keeping a lot of concentrated sulfuric acid around my house. So anyway, we are on to Voltaic cells, which is kind of a fancy chemistry way of saying batteries and stuff, right? There's a few different types of cells, but we're going to look at Voltaic cells. It's section 18.2 in your book. Let's go ahead and pause me for a minute and grab your book and get it open to 18.2 because we will reference some tables and stuff in there that we'll need. And I don't have all those. I can't scan stuff and all that kind of right at home. So anyway, oxidation reduction reactions are put to work. What we're going to do is we're going to separate a redox reaction. So like in the end of the last video, I just went ahead and threw the methanol right on top of the permanganate. There was nothing for that energy to do. First law of thermodynamics is energy can't be created or destroyed. So if we didn't do any work with that, poof, it all turns into heat. So boom, we saw a whole bunch of heat. So what we want to do with a voltaic cell is we want to separate those reactions and then turn all of that heat into work, right? So we have to do it in a slower system. Some thought processes we can put with that is, oh, you know, when I use my cell phone a whole bunch, it gets warm. Well, that's waste energy, right? So the less that happens from an engineering point of view, the more battery life your phone has and all that kind of stuff, right? So galvanic cells or voltaic cells, those terms are pretty much interchangeable, is a device that's going to transfer electrons through a redox reaction through a wire so we can make use of that energy. If we don't make use of that energy, then we turn it into a fuse and just generate heat and that kind of stuff, right? There are going to be some parts to our voltaic cell. There is an anode. There's a cathode, just like, you've heard those terms on batteries, I would assume. Easy way to remember this is vowels and consonants. Oxidation happens at the anode. Those both start with a vowel. Reduction happens at the cathode. Those both have a consonant, right? Also, oxidation is losing electrons, right? So if you want to not do it that way, you can say, well, when I'm losing electrons, those electrons have to go somewhere. The electrons are going to be generated where the oxidation half takes place, right? And cathode is reduction. So that's where you are gaining electrons. That's where the electrons are going to go to in your reaction. We also have to have a salt bridge. When you start moving charges around, if I move electrons from one place to another, I'm moving a negative charge from one place to another. Well, if I move a negative charge from one place to another without moving a positive charge, you're going to get a charge buildup pretty quick, and your reaction is just going to stop. So the salt bridge is to balance out your charges. So if you have negatives flowing that direction, well, you're also going to have some positives flow that direction. And if you have some negatives flow away from one direction, then you're going to have some negatives flow that direction, but they're ions. So you put a salt bridge in, which is usually a nice inert thing. You don't want something that's going to do a lot of acid-base stuff. You don't want it something that's going to do a lot of like precipitation reactions or whatever. So something like sodium nitrate is really good. You see potassium nitrate. Chlorides aren't quite as good because they will precipitate with some leads and some silvers. So we try to avoid chlorides, but you see it sometimes too. In my head, when I first learned these, I pictured a salt lick basically stuck in these things, right? Like a cow salt lick, but like it was U-shaped. You'll see the picture here in a minute. It's not a solid salt bridge. It is a salt bridge that's a solution. And it wasn't until like years later, actually, that I realized that I was picturing it wrong because you couldn't have migration through a solid salt lick kind of thing, right? So solution-y kind of thing still is what we're talking about there. So as we look at a picture of one of these guys, we have usually, it doesn't have to be two metals, but usually it's a couple of metals separated by a wire. And then you've got your salt bridge here. This is the thing that's like you'd have a cotton plug and a cotton plug and then a solution of your salt stuff. So it could migrate through the cotton plug, but it wouldn't go like crazy, crazy fast kind of thing, right? And so the electrons would go through the wire and the ions would go through the salt bridge. So we look at this one, and what's happening is silver ions are turning into silver metal. So this silver electrode would get heavier over time, and the solution of silver ions would get depleted, and your lead would get eaten away at and turn into lead plus 2. So your lead solution would get more concentrated. As that happens, is every time you go from a lead to a lead plus 2, you generate 2 electrons. Those 2 electrons then have to go somewhere. So they're going to run through this wire. There is energy, right? There's a delta G associated with this. In whatever direction it's going to run, it's going to release energy. And if we hook it up to some sort of job, right? A light bulb, a motor, whatever, a voltmeter, and just measure the voltage, we can figure out what that does, right? So this is a voltaic cell, right? Electrons are going to flow from the anode to the cathode. Negative ions are then going to flow from the into the anode side of the cell, right? Since the electrons are flowing out of there, you need to replace that negative. That negative is then going to the cathode side, so you're adding negatives there, so you're going to have to balance that out by adding positive ions in that direction, right? So here we have electrons flowing this way, so that means we would need to have negative ions flow into this cell, and we're losing negatives over here, so we would have negative ions flow into the cell. Did I say positive ions in the cell? Right? Since electrons are going this way, we need positive ions to flow into this cell because you're losing your positive ions here too. And here you are gaining new positive ions and losing electrons, so you would have negative ions flow into this cell, right? Let's see. So numbers-wise, right? So let's look at this one numbers-wise first. So if you go in your book to a magical page of 845, 845 has that page on it. So if we look at that page, we can find those reduction halves, right? These are written as reductions. Well, one of these is an oxidation, but they're all written as reduction halves. So if we look at the silver plus to silver ions on here, right? We go to silver plus to silver ions. I find that about halfway down on the left side there, page 845, about halfway or about 3/4 of the way down on that side, you have silver going to silver plus. So Ag plus an electron goes to silver. And the reduction potential there is 0.8. Well, that silver is getting reduced, so that's just fine. The lead is getting oxidized. So when we find the lead one, it's going to look backwards. So we find the lead one on here, and there we go. It's on the right side, and it's about 1/3 of the way down. And that is written as Pb plus 2 electrons go to Pb. And the reduction potential there is negative 0.13. But that's not what happened. What happened was the reverse of that. Think Hess's law. If Hess's law, what happens whenever we flip something in Hess's law, what do we do with the energy? We flip it. So the reverse of this reaction that we wrote down happened. So I'm going to flip that sign. And then I would just add those two voltages together. 0.93 volts is the voltage of this cell. So you could generate 0.93 volts by doing this cell. And that's the voltage. You might be sitting there thinking, whoa, Mr. Fred, you forgot something. What might somebody be thinking I forgot? They're probably thinking, hey, you forgot about the balance thing, right? There's 2 electrons in these leads, and there's a 2 here. I should double. Nope. Everywhere else, when these coefficients kind of matter, right? With electricity, or not with electricity, with delta E or delta H's, delta G's. They matter in kinetics, but only in the rate determining step and that kind of stuff. But here it happens the voltage happens 1 electron at a time. So it would affect the mass of the electrodes changed and the concentration changed, but it wouldn't affect the voltage on those. So that's that, right? So that would be the voltage for that cell. We look at this one. Why don't you pause me and figure out what you think the voltage for this cell would be. You've got zinc and silver. Figure out which thing is happening in which place and all that kind of stuff. And then I'll come back and walk you through it again real quick. So hopefully you've already figured that out. The silver is just the exact same as it was before. Silver is still getting reduced. It is on the cathode side. Reduction happens on the cathode side. We are going from silver ions to silver. On the anode side, we're going from zinc to zinc ions. Well, the zinc is there somewhere. I just saw it a second ago, and then I forgot where it was. Feel free to grumble at me. I can't hear you, so you can cuss at me, whatever you want. Right? So there we go, negative 0.6 or negative 0.76. But it is written as a reduction half, and this is the oxidation that's happening. So we are going to flip that sign. 0.8 plus 0.76 is 1.56 volts. 1.56 volts, right? You'll notice these voltages kind of match up with about your average alkaline batteries and stuff like that. There are things you can do to mess with it, concentrations and whatnot that we'll get to later, but that's kind of how that works. We tend to get lazy with stuff in chemistry. I don't know if you've noticed that, but we don't like to write out all kinds of stuff. So this is a way to what we call line notation. With line notation, you write your anode, and so you do your metal, and then you do the oxidized version of that. So it's losing electrons here. Then you do your salt bridge, and then you do the solution and your cathode. So you do anode to cathode. You separate it with the salt bridge. That's a two-phase boundary there, right? Whereas these little lines are one-phase boundary. So this is just showing zinc. Your reactants are written first, zinc and copper, and your products are written second, but we're like separating them out. So it's just like a faster way to write it so you can focus on one thing. So it's zinc going to zinc ions, copper ions going to copper metal, and so on. That's a pretty standard battery. Like when I did science and tech, I would actually have the kids make that battery, and we would actually sometimes in AP chemistry, it doesn't take but 5 minutes. We'd make one of those too. It only takes a minute. You just basically take the metals and separate them with like a wet filter paper that has some ions in it, right? Like a sodium nitrate separation thing there, and it's and then dip it in the solution. So that's that. We'll come back, or there's a little animation to look at after this. I think that's helpful. We'll probably come back. I don't know. I've always done these on the board and stuff, but we'll come. I'll try and figure out maybe if we can find a fillable thing or a FET simulation or something like that. So anyway, that's Voltaic cells, which is kind of a big chunk of this chapter.